GMAT all day.
You will hear me say over and over again that I think of the GMAT as a logic test. I do not think of it as a math test. I do not think of it as a verbal test. And I certainly do not think of it as a memorization test. And I think the people who try to turn it into a memorization test tend to struggle mightily with it. So what that means is when it comes to things like your exponent rules, even though I absolutely think you should have them memorized, it is not as simple as just memorizing them and plugging them in to whenever you see an exponent problem. You still need to use judgment about how and when to apply your exponent rules, and you usually have to use them in conjunction with other principles. And so you need to think of your exponent rules as just being one tool in your toolbox to be used in conjunction with other things, such as factoring, which we will look at in this problem, in order to achieve whatever your end goal is. And so it is a good idea when you are approaching a problem to always think, and if you're thinking about what should I do next, well, think about what you ultimately want to achieve. And so for a question like this that says if x and y are integers such that 12 raised to the x plus 12 raised to the x minus 2 all over 29 raised to the y is equal to 60 raised to the y, what is the value of x? And so we have been doing these problems where we have to solve for variables in our exponents, and our goal has been, I want to get the two sides of my equation to match. I want to get the bases on each side of my equation to match each other. And so if I were to get to a problem like this, I would not necessarily see in my head each step and where it's going to lead to and what the final answer will be from the beginning. But if I start just thinking, okay, so what is the next thing that I should do? Or in this case, what is the first step that I should take? If my end goal is to get the two sides to match, well, the first thing I would do is take care of the easy stuff first. I would say I have a fraction on my left side here. I have a non-fraction on the right side. I'm just going to move this 29 raised to the y over. I'm going to multiply each side by 29 raised to the y. So I get 12 raised to the x plus 12 raised to the x minus 2 is equal to 29y raised to 60 raised to the y. So now I no longer have a fraction on the left side. My two sides still don't really look that close to each other. I don't have many bases in common on my left and right side. I do have two 12s over here. So now if I'm thinking what to do next, so if you go back and if you remember our exponent rules, which you absolutely should, here I am multiplying, on my right side, I'm multiplying exponents with the same power, but different bases. And we said that I can take this and I can write 29 raised to the y times 60 raised to the y as 29 times 60, all raised to the y. And the question is, though, would you want to do this? Just because you can do it does not necessarily mean you should. And I would say in this case, I wouldn't want to do this because I have 12s over here. So now what I'm doing is I'm getting a base here that's going to be something in the thousands. It's going to be close to 1800. And so I don't want to be doing that. If anything, I want to be breaking down these guys. I need to get these guys to match up with these 12s over here. And so I probably would not want to do that. Instead, what I might say is, well, I have a 60 here. And I know within that 60, there is a 12 because 12 times 5 is 60. So 29 is prime. I cannot really do anything with that. So I might rewrite this, though, as instead of 60 raised to the y, 12 times 5 raised to the y. So now I have at least 112 on my right side. Now I can distribute this y out. And I'm a little bit closer to my end goal. So another problem we have is not just that our bases on each side don't match up, but I am doing an addition problem on my left side here, while I am doing multiplication on my right side here. And so how do I take care of that? And so here on the left side, if we shift our focus to here, this is another place where people commonly, they get stuck. They know they can do something, or they think they can do something because they have two exponents. They have the same base. They both have an x in their power, but they're not sure exactly what to do. And so what people tend to do is they make up a rule here. So they will try to combine these by either adding the bases or adding the powers or multiplying the powers. None of those are things you can do here. The exponent rule that they are either making up or misapplying is when you have exponents with the same base that you are multiplying. There is no rule really when you are adding exponents with the same base. So you cannot really apply any of your exponent rules here. So what can you do? To look at that, let's think about if instead of giving us variables in my powers here, we had numbers. And so if I had something like 12 to the fourth plus 12 squared, this I can just rewrite 12 to the fourth as 12 times 12 times 12 times 12 plus 12 squared, which is just 12 times 12. So between these two terms here, I have two 12s. So I should be able, since they share two 12s, I should be able to factor out a 12 squared. And once I do that, to get back to here, to get to 12 to the fourth, I need another 12 squared here, then plus 1 to get to here. And this is totally legitimate. I don't really think of this as an exponent rule. This is just normal factoring. And so what do we factor here when we have variables? Well, we really do the same thing. You should factor out the exponent with the smaller power. So in this case, x minus 2, just like we factored out the 12 squared over here. I'm going to delete this to give ourselves more space. And so if I factor out this 12, the x minus 2, now we are sort of reverse engineering our exponent rules. So to get back to 12 raised to the x, we need to add 2 here. This should be a 12 squared, then plus 1 over here. So here I did two things. I got another 12 on this side over here, but I converted this addition problem into a multiplication problem. And that is one of the things you are doing when you factor something. I think that's one of the reasons factoring is so valuable, because if you can convert an addition problem into a multiplication problem, then you can often use your divisibility rules to help combine things or cancel things out, which is a very useful skill to have. If I was to simplify this left side, 12 squared plus 1, that is just 145. 12 squared is 144. So now I'm doing multiplication on each side of my equation. Still not quite where we want to be yet, but I do think I am on the right track, because I see I have a 5 here, and I know that there is a 5 buried in this 145 that I can pull out. Because anything that ends in a 5 will be divisible by 5. What is 145 divided by 5? 5 goes into 45 9 times. So 145 is 29 times 5, which is perfect because I have a 29 over here. And so now I just need to rewrite this as 12 raised to the x minus 2 times 29 times 5. And then I always like to arrange my bases in ascending order. This would be 5 times 12 raised to the x minus 2 times 29 is equal to 5. The y times 12, the y times 29 raised to the y. And now I have achieved my end goal. The two sides of my equation perfectly match up. And so now to solve for my exponent, so I can replace 5 is just the same as 5 to the first. So this means y is equal to 1, and y is also equal to x minus 2. And so the question is asking for, what is x? So this just means 1 is equal to x minus 2, x is equal to 3. So y is equal to 1, x is equal to 3. This question just as easily would have been asking us to solve for y, and we can solve for both x and y. The question is asking for x though, so that is C. Do not choose A, that is Y. And that would mean that you did all of the work, you spent all of the time to get this problem, and then you selected the wrong answer choice because you misread the question. So don't do that. The answer is C, 3.